This is a short little screencast to cover the question that everybody is asking here for the third quarterly test. What do you need to know? This covers modules 9 through 12, and there's quite a bit of stuff in here. You'll find that the test has a lot of different kinds of questions on it. There's usually only one chance per topic. And, since these are practice problems, they will be worth several points each. So try as best as you can to have all of these topics under your belt before you start taking this test this week. First thing you need to do is look over that chart of polyatomic ions and make sure you know what they are. What is NH4 with one positive charge? Ammonium, of course. Or SO4 with 2 negative charges, sulfate, not to be confused with sulfite. Make sure you go through all of those polyatomic ions. They were supposed to be memorized several modules ago, and if you work through any of the worksheets, you should have these under your belt. You need to be able to work both ways. So if I give you the name of an ion, if I say what is hydroxide, and you say, okay, that's OH, excuse me, with 1 negative charge, or if I actually write out something like, what is carbonate? So CO3, 2 minus. You have to be able to work both ways from just the formula, the name, and the chemical formula. The next thing you need to know are molecular shapes. You need to be able to figure out what shape a particular molecule is going to have. Is it linear? Is it a bent shape? Is it a pyramidal shape? Is it trigonal-planar? Or is it tetrahedral? And you might want to think about it this way. In a linear shape, you've got 2 electron areas. So there are double bonds or triple bonds. Forget what I'm spelling here. Areas. My stylus is not working. But there are 2 areas of electrons, and so they want to be as far apart as possible. So we've got our central atom here, and there'll be 1 area of electrons on this side and 1 area of electrons on this side and some other atom connected to it on this other side. But there's just 2 areas of electrons, and they want to be as far apart as possible, so they're going to be on opposite sides. To keep with that same way of looking at it, on a trigonal-planar molecule, you're going to have 3 electron areas because you're going to have a central molecule, and then there'll be electrons at 3 distinct areas. These are using up all of the electrons, so one of these has got to be a double bond, and then with the some other atom connected to that. So because there are 3 areas and there are no other places where there are electrons, these are all bonds between elements, it's going to form a flat triangle shape. Everything else, the bent and the pyramid and the tetrahedral shapes, are all based on 4 electron areas. And the bent shape has 2 bonds plus 2 lone pairs. So in this shape, you've got your central atom, and your electrons have bonded to something else for 2 of your 8 possible electrons, 2 of the pairs. And then the other ones are just lone pairs up here on top, and so they're forcing this bent shape by their electron repulsiveness. In the pyramidal shape, you've got 3 bonds, and then, of course, 1 lone pair. And to just kind of picture that, you've got your central atom, and it's going to be bonding out in 3 directions, and this is one of those ones that's supposed to be 3-dimensional. And then the lone pair will be sitting on the top, forcing everybody down, so that you've got 4 places where there are electrons, but 3 of them are tied up in bonds. And whereas compared to the trigonal-planar, all 8 electrons, all 4 places are tied up in bonds, whereas in this one, you only have 3 places tied up in bonds, and the 4th place is a lone pair. And then, of course, your tetrahedral, you've got 4 bonds possible there, no lone pairs at all, which gives you that shape that we can't draw without being 3D here in some way, dotted lines. So know these molecular shapes. Be able to identify what is likely to be the shape of a molecule given its structure. Then you need to know acids and bases, and I see I miss an S there. This should be acids, but since this is just a review, I'm not going to go back and redo this slide. You need to know how to write equations for when there is an acid and a hydroxide base. And a hydroxide, again, is that polyatomic ion, so it's something that's OH, like, say, our sodium hydroxide that we had when we made our soap. And then your acid, let's pick a very easy one, hydrochloric acid, HCl. So acids will donate a hydrogen in this situation. Hydroxides will donate the hydroxide, and as you end up as a result, you're going to get some kind of ionic salt plus water. So you need to know how to write these sorts of equations and realize your salt is going to be made up of what's left over, the sodium and the chloride. If it was first in the molecular formula, when it's on this side of the equation, then it's going to be first on that side because it's telling you it's a cation, has a positive charge, and so this is positive and then negative sodium chloride. Covalent acids and bases, these are not going to be giving you water, they'll be giving you two ions. And one of the compounds will be identified as being an acid or a base. So the acids in this case, just like in the hydroxide type of acid and base reactions, the acids will give up a hydrogen, and then your bases will be some particular molecule that's going to accept, so bases over here, will accept a hydrogen. And you are not going to make nice, tidy little neutral compounds like an ionic salt and water. You're going to end up making two ions. So in this case, one of these, the base is going to accept a hydrogen. It's going to accept just really the protons of that. So it's going to add an extra positive charge. The acid, which gives up the hydrogen, is losing a positive charge. And so it's going to end up being the negative ion. Then you need to know how to calculate molarity, how to do dilution problems, and then the special example of dilutions or titration problems. So remember, molarity is the big capital M, and it is the moles per liter of solution figuring. And whenever you need to know about moles, you need to go back to that periodic table and look up the information on how many grams there are in a mole and add up for all of the particular elements that are in a compound. You go back and do that stoichiometry stuff. And then you have dilution equations where you're considering the concentration, the molarity of one particular substance and the volume that you have of that solution, and you want to dilute it down to another molarity and another particular volume. Remember, on these equations, they are a dilution equation, and so you're going to be starting with a more concentrated solution. Let's just kind of, for example, let's say, this molarity over here is a molarity of 5.0, and you want to make something that's a molarity of 3.0 molar. And you're going to be wanting to make a certain amount of this solution. Say we want to make 100 milliliters of this solution. Then you're going to be trying to figure out how much do I need of this 5.0 molar solution. Obviously, you don't need 100 milliliters because it would then be all 5.0 molar. It would not be 3 molar, it would be 5 molar. So you're going to be getting a number smaller than 100, but in your problem, make sure you're telling me that you're adding water to bring it up to 100 milliliters. You're going to dilute this strong solution until it has been made weaker by adding more water. And the question is, how much exactly do you start with before you do the final dilution? Titrations look just like dilution equations, except here you're looking for a molarity of an acid and the volume of an acid as compared to the molarity of a base. This one of the, you're not knowing one of these factors in the volume of the base. So in a titration, you're taking a solution and adding, say you're starting with a base, you're adding enough acid to neutralize all of the base. And so by doing that, you can figure out how much base you had in there to begin with if you know your molarity of the acid. You need to know how to calculate changes in freezing points and boiling points. Remember, these are both colligative properties, and as you add more particles of a solute into a solution, freezing points will decrease and boiling points will increase. I will be giving you the constant for the solvent, so we're only working with water here. So the only thing you need to memorize is how the formula works. So remember, the formulas for these are telling you that your change in temperature is going to be equal to excuse me, a freezing point or boiling point constant that I'm going to provide for you, times the molality of the solution. And remember, with molality, that's small m, you are calculating based on moles of solute per kilograms of solvent. So make sure you've got your formula straight for molarity and molality. But then also you need to multiply in this formula a negative of the number of particles, which is given I, to remind you it's usually ions, but not always. So it's the number of particles that a solute will dissociate into, will fall apart into when it goes into solution. Remember too that this formula is giving you a change in the temperature, so that when we're talking freezing points, the normal freezing point for water is 0 degrees Celsius, and so whatever amount you get for a change, it's going to be subtracted from 0 degrees Celsius. The formula for boiling points is very similar. The constant is different, but again, I am providing that so you don't need to memorize it. But your change in temperature when it comes to boiling points is equal to your constant of boiling times your molality of the solution times the positive of the number of particles. Because the negative for freezing point reminds you that freezing points go down, and then when there's a positive number for boiling points, that's telling you that boiling points go up. So make sure you know these formulas and you know how to use them, and especially you know how to calculate molality. Then we get into our gas laws. We're not going to have you work with Boyle's law or Charles' law independently. You just need to do the combined one. So if you get a gas at a particular temperature and volume, then you need to be able to calculate what is that, some aspect of it at a new temperature or a new pressure or a new volume. And probably one of the key things to remember here is that temperatures are always in Kelvin units. You always have to convert them to Kelvin. You do not use Celsius even if Celsius is given in the problem. So don't forget that. You will also have a problem that will ask you to calculate the partial pressures of gases in a mixture. And in order to do that, you need to be able to figure out the mole fraction. Of course, let's say we have a mixture of gases of A and B. We'll just call them letter names, not specific gases. But gas A there's 4 moles in our sample of gas, and in gas B, there are 6 moles in our sample. And say that both of them together are producing 2 atmospheres of pressure. So the question would be, how much of the 2 atmospheres of pressure is being provided by gas A? So we need to figure out the mole fraction for gas A, and we do that by taking the number of moles of that gas, so there's 4 moles, and we divide that by the total number of moles in the sample. So in that case, we're going to have to add our 4 moles and the 6 moles together to give us 10 moles of total in total. And then go ahead and do the math with the numbers. That will give us a decimal of 0.4. That's our mole fraction. It doesn't have any units associated with it. And we take that amount, that's the part of the whole that's provided by gas A, and we would multiply that by the total atmospheres. So 0.4 of 2 atmospheres is the amount of pressure provided by gas A. If you go ahead and do the rest of the math, you'll see that 0.8 atmospheres is how much pressure, the partial pressure, provided by gas A. And finally, you need to be able to work with the ideal gas law, and you need to have this formula memorized as well. Remember, the ideal gas law is basically it's a combination of all the other gas laws put together into one equation. So we have Boyle's law, which is pressure times volume equals a constant. And you've got Charles' law that says volume divided by temperature equals a constant. And then we've got Avogadro's law, which we didn't talk about from your textbook, but I mentioned it in a previous video, which is the volume divided by the number of moles equals a constant. If you take these three laws and sort of overwrite them, you would get something that said, PV equals, or divided by NT equals a constant. And so we rewrite that for the ideal gas law as PV equals N, R for a specific constant when we need it, instead of the K that we tend to use in talking about these laws separately, and then T. So PV equals nRT is your ideal gas law, and if you can see how we've basically just combined all of the kind of, I don't know, you call them smaller gas laws or more specifically oriented gas laws into one specific gas law. The reason we use R for our constant is because it depends upon what units we're using for pressure, exactly what that constant is going to look like. And so I will always provide you with the constant to solve these problems. You do not need to memorize what the R value would be for atmospheres versus millimeters of mercury versus kilopascals. But you do need to memorize the PV equals nRT formula and know what all those letters stand for and be able to use it. So if you are comfortable with all of the topics that I've mentioned in this video, you should be ready for that third quarterly exam.